Okay, today we will be discussing particularly a one-dimensional box problem, which is the most important problem in quantum mechanics, right? And this is one of the exactly solvable problem in our quantum mechanics, right? And this is the problem we have. It is a one-dimensional problem, which is in one direction, which is x, and there is zero potential between 0 and L and infinity elsewhere. We can write this condition in the following way. That is v of x is equal to 0 to L and less than or equal to x less than or equal to L, right, and infinity elsewhere. This is the way in which we used to write these potentials mathematically, right? And this among these two conditions we can solve only one first condition, because for infinity we can't have any solution for this, right? And in order to solve this problem, we have to write as time independent Schrodinger wave equation, which is also called as a stationary state equation. This minus h cross square by 2m d square psi by dx square plus v psi equal to e psi. Okay, and for potential v is equal to 0, we write minus h cross square by 2m d square psi by dx square, and instead of v we put v is equal to 0, right? And here we have that Schrodinger equation. We write it as, by removing 0 we just wrote that equation, and on rearranging this 2m by h cross square into e psi, we get d square psi by dx square equal to minus 2m by h cross square e psi, right? And on putting that right hand side equation into left hand side, on replacing the sign with positive, we get d square psi by dx square 2me by h cross square into psi, right? And we put, in order to solve the second order differential equation, we are putting k square equal to 2me by h cross square, and we will get the differential equation in this form, right? Once you got this equation, you can write a general solution for the second order differential equation. Since it's a second order differential equation, you will be having two arbitrary constants, right? So two arbitrary constants for second order differential equation. Okay, in order to check whether this solution is a valid solution or not for the above mentioned differential equation, just substitute that equation by taking second derivative and substitute that into this equation, right? This equation, right? This second, take a second derivative, instead of d square psi by dx square, write that second derivative, and k square instead of psi, substitute this, right? You can get a solution, right? And here we have two constant a and b, which are arbitrary constants. For a second order differential equation, we'll be having two arbitrary constants. Okay, these are the two boundary conditions, right? As for first boundary condition for this boundary, and second, psi of L is equal to 0, that is the wave function is 0 at that boundaries. That's what the boundary condition tells you, right? And here we have, on applying first boundary condition, we write, instead of x you just substitute 0 there, and the wave function is 0, and we know sine of 0 equal to 0 and cos of 0 is equal to 1. So using that, we can get b is equal to 0, right? This is the way we used to find b equal to 0, right? On applying second boundary condition, we write, instead of x we substituted L, that's what the boundary condition is, and instead of x we used L, and from previous boundary condition itself we find b is equal to 0. Then we write a sine k of L plus 0 equal to 0. So this is the second boundary. On applying second boundary condition, we got this equation. It's obviously a should not be 0, so sine k of L must be 0. So we can write sine k of L is equal to 0, and similarly sine n pi is also 0. Whatever may be the n value is, the sine pi will be 0. So that's why we are equating these two terms, sine k of L and sine n pi, right? And since we have a common trigonometric function, we write it as KL is equal to n pi, right? And sine k of L is equal to sine n pi equal to 0, and we write KL equal to n pi on writing k n pi by L. Okay, and this is the wave function On solving the value of k, we wrote psi of x is equal to a sine n by L into x. Okay, where a is a constant, we can find we will be finding that by normalizing these the given wave function, right? This is a normalization condition which is given as integration of minus infinity to plus infinity psi star psi dx equal to 1. This is the wave function psi and psi star. And for this problem we will be writing 0 to L psi star psi x dx equal to 0, right? This is the boundary condition for this problem, right? And we, on substituting the values of psi and psi star, we write this equation, right? And on just multiplying these two terms, we write a square integration of 0 to L sine square n by L into x dx equal to 1. And we know this formula, sine square x is equal to 1 by 2 1 minus cos 2x, right? On substituting that, you will get this term, and you will be taking this constant outside, right? Constant outside, we will be writing a square by 2 and remaining terms there. On integrating, and this will be sine here, okay, this will be sine here, so please consider it's a sine, okay. And applying limit, what happens, this term will vanish, and on applying boundary condition, a square L equal to 2, sorry, this is 1 here, okay, this is 1 square is equal, sorry, this is 2 only, because this 2 is taken this side, 2 a square L equal to 2, and on rearranging, a square is equal to 2 by L and a is equal to root of 2 by L, and the normalized wave function can be written as root of 2 by L sin n by L into x, right? Once we solved once we got normalized wave function, we will be finding the value of E, that is the energy eigenvalues. With k square equal to 2m E by h cross square, we can find that this equation in a second slide. And in previous steps, we found k square equal to n square pi square by L square. So we are equating these two terms, and we will be writing E square equal to h cross square n square pi square by 2m L square, right? And this is the energy eigenvalues and eigenstates for 1D box and probability density of a wave function, right? And the energy difference between uh, consequent energy level is given as 2n plus 1, okay, 2n plus 1. And these points, the nodes, in that node points, you can find the probability of, you can't find the particle, so probability of particle is 0 or very less in this node points. Similarly, the maximum probability of finding a particle is can be probability of a particle finding a particle is more in this regions, right? In this region you can find the probability is more. The peaks we have more probability, and in this nodes you have very less probability of, or zero probability of finding a particle, right? Thank you.